Well, good day. Welcome back. Well, I have an assortment of abacuses. Abaci, maybe? Well, we have the most modern version of the abacus, the Japanese soroban, which has one bead above the bar in the heaven area, four beads below the bar on the earth area for each rod. That's the 1-4 soroban. We also have a 1-5 soroban. So this is the older version that came out of favor probably in the early part of the 20th century, where there's 5 beads per rod below the bar instead of 4. And then we have the traditional Chinese abacus, which is pronounced something like suan, and it has 2 beads above the bar and 5 below the bar for each rod. And the construction design is different than the Japanese soroban. The Chinese one uses these more rounded beads, and typically the construction is not quite as high of a caliber of craftsmanship as the Japanese ones. And then there are some hybrid abacuses. So this is a 2-5 abacus, but the beads are the Japanese soroban style, the biconic, diamond-shaped, if you want to call them that. And the construction of the frame is more of the Japanese style, even though it's a 2-5. And also this version, they've colored the beads, different colors on each rod, probably to help with people who are learning the abacus. Well, each of these versions of the abacus, the 1-4, the 1-5, the 2-5, each of them have their own advantages and disadvantages when it comes to operating them, mainly like addition and subtraction. So I'd like to cover some of the differences between them, and then we'll talk about this one. Stay tuned. Well, first of all, we could look at this assortment of abacuses from a historic perspective. The 1-4 abacus actually goes all the way back to the Roman Empire era, but they weren't using wooden beads threaded on rods. They were using clay balls in grooves, or they were using counters on a flat table with lines marking the place values. And they got that version of the abacus from the Greek, which in Latin, abacus literally means a flat surface. The Chinese somehow got the bead frame calculator. There's speculation they got it from the Romans. But the Chinese added more beads per rod because of their monetary system. Part of it was base 16. They needed to be able to enter 0 through 15 on each rod, which is why we have 2 5 beads and 5 1 beads. The Japanese inherited the Chinese bead frame calculator in the maybe 15th or 16th century, and very soon after doing so, they make some changes to it. They change the shape of the beads to this biconic shape with the ridge, and they get rid of the second 5 bead up above, so they have this 1-5 configuration. And they kept that configuration up until, say, the early 20th century, when they removed the 5th 1 bead to make it the 1-4, the modern version. And it's probably a good speculative idea that the reason why they did that is because after about 1860, Japan was heavily interested in industrializing. And an abacus that could do 0 through 9, basically mathematical arithmetic numbers rather than currency numbers, made more sense in an industrial society involving industry and science and technology, which is probably why they got rid of that 5th 1 bead down below. Okay, so that's kind of like a little historical overview, but there are differences in the way each version works in terms of how easy it is to use. So every time I'm doing an abacus video, I think it's important that I review the basics of the modern 1-4 soroban in terms of addition, at least. So you have 4 different kinds of number problems with addition and subtraction. The first kind is direct number entry. Problems like, 1 plus 3, 2 plus 6, 3 plus 6, 2 plus 5, all of those kind of numbers. The 2 numbers can be added together directly without any additional complication. And then, if both numbers are less than 5, but you can't enter them directly, like 3 plus 4, for instance, but you don't have 4 additional 1 beads, then you have to do a 5's complement. So you have to subtract the 5's complement of 4, the number you're adding, and the 5 complement of 4 is 1, and add the 5 bead. for example. So that's a 5's complementary problem. And then you also have a lot of problems that are 10's complements problems. For instance, 3 plus 8. I enter 3. I don't have 8 left on this rod, this column. So I'm going to have to enter a 10 over here and subtract the 10's complement of 8. So the 10's complement of 8 is 2, add the 10, and the answer is 11. So that's a 10's complement problem. And then the fourth kind of operation that you can get into is in the case of, let's say, 6 plus 7. You enter the 6. We know it's not a direct 5 complement operation because the two numbers are bigger than 5, but we don't have 7 left on this rod to directly add, so we're going to have to do a 10's complement. But the 10's complement of 7, which is the number we're adding, we can't take away 3, which is the complement. We don't have 3 1 beads. So we have to do this intermediary of, in order to take away 3, we have to do a 5's complement subtraction problem, which is taking away 5 and adding the 5 complement of 3, which is 2. Now we can finish the 10's complement by adding the 10. So that's like a nested complementary problem. It involves both 5's and 10's complements. And those are the most complicated problems with addition and subtraction. And by the way, the shortcut way to think about this operation, like in the case of 6 plus 7, is when it comes to adding the 7 you could think of as being composed of 2's and 5. And so what you do is you push the 7 up. You're pushing up a 2 and a 5, and then add the 10. That's a little bit easier way of thinking about it. But those are the 4 different kinds of problems you'll encounter when you're doing addition and subtraction with the abacus. Okay, so the 1-4 abacus requires you to do the most kind of complementary problems. But some of the other versions of the abacus require less complication because they have more beads per rod. Well, let's start by talking about the Chinese 2-5 abacus that they call the suan. So when we think about decimal notation and decimal numbers, Arabic numbers basically, we want to have 0 through 9 on each place value. The thing with the 2-5 abacus, though, is you can represent up to 15, a value of 15 on each rod, each place value, which we would say is irrational or not rational with respect to decimal numbers. So when we're doing things like addition, for instance, it's easy to add two numbers together without having to use any complements. So of course, you have problems like 2 plus 2 or 6 plus 3, but you can do things like 8 plus 7. And when you end up with that sum, you have to rationalize it in order for it to be a number with 0 through 9 on each row. And the way you rationalize it is from the left to the right, top to bottom. So we would start with the 2-5 beads and replace it with the 10 bead on the next row there. And then these 5s, we would take it away and represent it with a 5 bead there. So the answer is 15. So the advantage of the 2-5 is we can enter a lot of problems directly with two numbers, like 8 plus 6. And then I rationalize it by converting those two 5s to a 10 to see my answer of 14. Whereas if you were using the modern 1-4 soroban, for example, 8 plus 6 is going to be like 8, and I don't have 6 beads. I have to do this nested complements problem of pushing 6 up and adding the 10 to get the 14. So there's a little bit more mental work involved in the more compact soroban or abacus that has fewer beads. Whereas the 2-5 abacus requires fewer of those kinds of complications. However, the potential downside to the 2-5 abacus is when you're doing a lot of straightforward subtraction and addition problems, having the extra bead can get in the way of your calculations, especially if you're using complementary arithmetic. It can be a distraction, at least it certainly is to me. I don't mind as much the extra bead up on top here, but having that 5th bead down here, like, for instance, like 2 plus 3, I have to now rationalize it and before I can continue, right? Whereas if it was a 1-4 soroban, I enter the 2, and to do the 3, I do a 5's complement. Subtract the 5's complement, add the 5. There's the sum. So it seems like with a lot of these abacuses that have extra beads, you can eliminate having to do a lot of complementary operations, but at the sacrifice of having to do this rationalization afterwards. And it kind of depends on what you're comfortable with. What causes your mind to be confused around operating the abacus might determine which type of abacus is best for you. Now, when we have the 1-5 abacus, what we discover is that we can do a lot of the problems directly that would normally require a 5's complementary operation. So any problem that adds up to a total of 5, we can enter it directly, like 1 plus 4, 2 plus 3, 3 plus 2, 4 plus 1. All of those operations we can enter directly and then rationalize it afterwards by regrouping it, representing the 5 as a single 5 bead if we need to. Having a single 5 bead on the top means that we still do have some of our complicated or more complicated complementary steps, like 7 plus 6. You're still going to have to do the push 6 and add the 10, for instance. And of course, you do have the 10's complementary operations, like 3 plus 8. 3 to add 8, you have to subtract the 10's complement, add the 10, right, to make 11. So you still have 10's complement problems, but you can eliminate most of the 5's complements problems by using a 1-5 soroban. So it depends on, again, what part of abacus operation your mind has a problem with comprehending. So for you, maybe the 1-5 might be a better device than the 1-4 or the 2-5 for that matter. Now, there are some kinds of operations where having the extra beads of the 2-5 abacus can actually be an advantage. One of those operations is involving subtraction, where you have a lot of borrowing going on. So to show you this problem, we'll assume that this rod is the units rod. So units, tens, hundreds, thousands. So let's say we have a number like 10,003, and we want to subtract, let's say, 8 from 10,003. What we can do is we can first take this 10,000 and represent it as 10,000 here. So we aren't really changing the number, we're just regrouping. And then we take one of these thousands and regroup it as 10 hundreds, and we can take one of those hundreds and regroup it as 10. And now we're going to subtract 8. We can now do a 10's complement subtraction problem. Is we subtract 10 and add the 10's complement, which is 2. And now what we need to do is re-rationalize the number, so we just take the 5s and replace it with a 5 bead. And the answer is 9,995. And so there's an example where having those extra beads enabled us to do this borrowing much easier. It was very rational, easy to understand. We didn't really have to keep any numbers in our head and try to remember things. The abacus did it for us. And that's one of the advantages of having the extra beads, being able to represent 10 on each row. And incidentally, you can do that same operation on the 1-5 abacus, because each rod you can represent 10 of its value. So if you have that problem of like 10,003, I think it was, and we want to subtract 8 from it, well, we can take this 10,000 represented as 10 thousands and take one of the thousands represented as 10 hundreds and take one of the hundreds and represent it as 10 tens, and now we can do our subtraction. So we're going to subtract 8. We're going to basically add the tens complement and subtract 10, and then we rationalize the number, and now we have 9,995 as the answer. So any kind of abacus where you can represent a whole 10 on each rod, you can do these subtraction problems that would normally require a lot of borrowing. You can do them a lot easier, conceptually easier, without having to remember things. So now we get to this abacus. So this was originally another one of these 2-5 soroban style 2-5 abacuses. In other words, a Japanese swan pond built as a Japanese abacus with Japanese style beads and a Japanese style frame. So what I've done here is I've been playing around with the abacus and I've decided that I'd like to experiment with a 2-4 configuration. But the problem is nobody ever made a 2-4 abacus as far as I know. I mean, there may have been craftsmen hundreds of years ago that tinkered around with the idea of it, but nobody's ever built one as far as I know. At least none have survived. And so what I've done here is I've made out of stiff cardstock this little paper insert that has these little slots cut where each rod is, and it basically just fits over that last bottom 5 bead or 1 bead in order to conceal the 5th 1 bead and to enable us to have a 2-4 abacus. Now, what's interesting about the 2-4 abacus is it has a lot of the same efficiencies of the modern 1-4 soroban because you only have 4 1 beads per rod, but it enables you to do those nested complementary steps without using the complicated method of thinking about it, like our example of 6 plus 7. Well, we have an extra 5 beads, so we can actually enter the 7 directly and then simply rationalize the result, taking the 2 5s and making it into a 10 bead. So this particular version of the abacus, we actually dispense with those nested complementary steps. I mean, we still have individual 5s complements. You know, like 3 plus 4, there's 3, and to add 4, you do the 5's complement of 4, which is subtract 1 and add a 5. So you still have 5's complements, and you still have 10's complements, right? Like 8 plus 3, so there's 8, and to add 3, well, you can do this one 2 different ways. You can either subtract the 10's complement of 3, which is 7, and add the 10, or 8 plus 3, you can do it as a 5's complement problem. Add the 5 and subtract the 2, which is the 5's complement of 3, and then you have to rationalize these 2 beads into a 10. It's interesting, the 2-4 abacus, it's a different version that nobody's really played with much, as far as I know, but it does enable you to do a lot of these more complicated problems without thinking as much, because you can enter a lot of different pairs of numbers directly. So you can represent up to 14 on each rod. So that gives you the ability to do a lot of combination problems that normally would require the nested complements. You can do it directly. Remember that subtraction problem? Here's our units. We're going to put 3 10s, 100,000. So we're going to do 10,003 and subtract 8. You guys remember that problem? Can we do the borrowing, the subtraction on this? Well, let's see. We can take away the 10 and we can represent it as 10. And we can take away one of those and represent the next one as 10. And we can take one of those and represent the next one as 10. And now we want to subtract 8 from this, so we're going to add 2, which is a 5's complementary problem, and subtract 1 from this column, which will be like that. So yeah, you can do that complicated subtraction problem that involves borrowing. You can do that on this abacus as well, because you can represent 10 on each rod. So I find the 2-4 abacus is kind of a cool idea. The problem is, of course, that nobody made these. And so what you might have to do, find yourself a 2-5 abacus and make yourself a little cardboard baffle to put into it to convert it into a 2-4 abacus if you want to do that. Well, I've covered a wide gamut of different styles of abacus, and of course I have a collection of abacuses. I've collected them over the years, but you might not have a collection of abacuses, and you might be thinking, Joe, I don't really know what style of abacus I would really like to play with and learn. And I know that to answer that question, first of all, the 1-4 abacus, the modern version, is the most common that you'll see on Amazon and other online sellers. And there are people selling this version of the Chinese, the 2-5, but I don't really like the build quality of these style of abacuses with the round oval beads. They're not nearly built as well as the Japanese versions. So I really do like the 2-5 abacus with the biconic Japanese style beads, like this colored version, or the version here that I modified. And so if you buy like a soroban style 2-5 and you make one of these cardboard cardstock baffles, you can turn it into a 2-4 abacus like I've done here, but you could also flip it up and stick it up here and hide the second row of 5 beads, and you could turn this into a 1-5. Or you could make 2 of these cardstock baffles and turn it into a 1-4. And what I'm suggesting is then you only need to buy 1 abacus. If you have big hands, make sure you get one with bigger beads like these are. Don't get the ones with the tiny beads for children or for students. So it'll be easier for you to operate. But you could buy just a 2-5 with soroban style beads, make one of these little cardstock baffles, make 2 of them if you need, and you could modify your abacus to be either a 2-5, a 2-4, a 1-5, or a 1-4, all with just 1 abacus. So then you don't need to collect abacuses. And that wouldn't be any fun, would it? Actually, it is. A lot of fun collecting abacuses because you can collect dozens and dozens of them and they'll fit in a plastic bin. They don't take up that much room compared to collecting, typewriters or British sports cars or something. So there's my suggestion. If you're new to the abacus world and you want to experiment with it and you don't know what style of abacus, because once you start learning how to do like addition and subtraction mainly, you might find that certain kinds of operations are more difficult for you to easily do on certain types of abacuses. Maybe the 1-4 is a little more complicated than what you'd like to do. So maybe you do want to start out with a 2-5 and it makes it easier initially. And then you could put one of these cardstock baffles and change the layout, right? Hide a row of beads and make it into a different machine, basically. Well, these are some ideas for you if you want to get into the hobby of learning the abacus, which is not only about learning how to operate it, but it's also collecting them and noting the differences between the Chinese and Japanese build quality and reading up about the history of the abacus. It goes back thousands of years, for instance. So it is a fun little hobby to do. And there's only like a handful of us in the world that are probably abacus hobbyists. But hey, you could join our micro cultural group of abacists. Maybe we should start an abacus guild. In any event, I wish you the best in your journey with the abacus. It is a good way for older folk like this brain here to keep us a little bit sharper by just running through and doing practice exercises like add 1, 2, 3, 4, 5, 6, 7, 8, 9 and add it 10 times, for instance, and you'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, and you'll have done all possible combinations of all the addition problems. Or you can do it in threes. You can do just add 1, 2, 3 to itself 10 times, and then add 4, 5, 6 to itself 10 times, etc. Those are little drills you can do throughout the day in your spare time just to keep your mind sharp, and it really is kind of fun to do. Okay, I'll leave you with that. I wish you the very best with your creative ventures, and as always, stay creative and have yourselves a great day, and bye-bye for now.